Hello everybody. Let us now move on to module 6 of EC206 computer organization. We are now looking at the various kinds of memories that we had started studying in module 5. So today's topic consists of the cache memory. Let us review memory hierarchy which we had studied in module 5. If you all remember this picture from module 5, this figure shows the various memories arranged in the form of a hierarchy. The first level of the hierarchy is the cache memory. So the cache memory is sitting in the same chip as the processor. It is as the CPU. It is sitting very close to the CPU. So the cache is a small and fast memory and it is inside the processor chip. So the time required to access data from the cache is very, very low. If the required data is not available in the cache, then the processor looks for it in the main memory. So the processor is going to go to the main memory and look for the data. The main memory is larger than the cache memory, but it is also slower than the cache memory. Now, if the required data is not available in the main memory, then it goes to the hard disk, that is the virtual memory. This is a very large and a very slow memory. Now looking at the concept of the cache memory, we saw from the previous diagram that the cache is located inside the processor chip. It is there inside the processor chip. It is very small and very fast. Okay. So the reason why we use a cache is so that with very little memory access time, the CPU or the processor can access commonly used data. So it is commonly used data that is stored inside the cache memory. So the number of data words that the cache can hold is called the cache capacity C. Okay, so the number of data words the cache can hold is called the capacity C. And obviously the cache is smaller than the main memory, so we can say that the capacity of the cache, the number of data words it can hold, is smaller than that of the main memory. So let us see what happens once again. When the processor tries to access data, where does it look for? It first looks in the cache. The cache is situated right next to it, so it looks in the cache. If the cache hits, remember the terminology hits and misses from the module 5. Cache hits means the data is available in the cache. Whatever data the processor is looking for is available in the cache, and that data is available to the processor for immediate use. Now, if the cache misses, what is cache miss? That is the data that the processor is looking for is not available in the cache, then it has to look for it in the main memory. All right. So if it finds data in the main memory, not only the processor uses that data, it fetches the data from the main memory and places it in the cache for future use. Okay. So there is a concept called temporal and spatial locality on which the processor decides, which we will be studying a little in detail later. So what the processor thinks is that if I need the data right now to use, I may need it in the immediate future. So when it fetches the data that it did not find from the cache from the main memory, it not only fetches it and uses it, but it also places it in the cache for future use. Now the cache, as we know, is a small memory. So to accommodate the new data, the old data must be replaced. So now there are two issues to be considered. Now, what is the subset of the main memory? See, all the things cannot be placed in the cache. Most of the data is available in the main memory. Okay, so what is there in the cache is actually a subset of the data that is in the main memory. A copy of the data that is there in the main memory is kept in the cache. So what subset, that is what of the data, which of the data words in the main memory should be kept in the cache? That is something that has to be considered. Okay, and we had seen, no, to accommodate the new data, old data must be replaced because the cache is very small. So which is the old data that should be replaced to accommodate the new data? These are the issues to be considered in cache memory, which we will be dealing in each of the subsequent lectures. Continuing with the concept of cache memory, cache is organized in different ways. Okay, so before we study the different ways in which cache is organized, let us look at the parameters that characterize caches. So some of the parameters that characterize caches are capacity C, which we had already seen. What is C? C is the number of data words the cache can hold. Then the next parameter, number of sets, S. So the data words in the cache, okay, the data words in the cache are organized into a number of sets. So The cache has a number of data words. The number of data words is called C, and the C data words are organized into a number of sets, and the variable for that is, or the parameter for that is S. So next parameter is the number of blocks B. Each set holds one or more blocks. Okay, so the cache is organized into a number of sets. Inside the sets are one or more blocks. So you have the full cache C. Okay, then that C words are organized into a number of sets S. Inside each set there may be one or more blocks. The number of blocks is called B. Okay, now block size B is, in each block how many data words are there, that is called block size B. So capital letter B is the number of blocks and small letter b is the number of data words in each block. So you can see number of blocks B is equal to C divided by B. Okay. So B, the number of blocks, this number of blocks B, here we had said each set holds one or more blocks. But what is the total number of blocks in the entire cache? That is given by the cache capacity C divided by B. So the number of blocks in a set is called N. Okay. So there's a difference. What is this? The number of blocks B is inside the cache. Totally how many blocks are there? That is given by the cache capacity divided by the number of blocks. Okay. Inside each set, how many blocks are there? That is given by the value or the parameter N. Now, very important term is called mapping. So mapping is the relationship between the address of data in the main memory and the location of that data in cache. We said that in the main memory there is data and a subset of that data is available in the cache for immediate use by the processor to make the access times low. Fast it wants to get the data, so a subset of the data is there in the cache. So there should be a link between the address of data or a relationship between the address of the data in the main memory and the location of the same data in the cache, and that relationship is called the mapping. Okay. Now a very important thing we have to remember is that each main memory address maps to exactly one set in the cache. We said that the cache is organized into a number of sets, but there is a unique mapping between a particular main memory address and the sets in the cache. That is, one main memory address can go to only one of the sets. That is, there's a unique mapping over there. Okay. Now, which set it has gone to? So we know that memory data words are addressed using address bits. Okay. Now in MIPS we had seen that the number of address bits is 32 bits. Some of these address bits are used to determine which cache set contains that particular data. So once again, let us see, each memory address maps to exactly one set in the cache. Okay. And some of the address bits of a particular data word in the main memory are used to determine which is that set, exactly one set, no, which is that set which contains this particular data. Now, a set may have more than one block, it may have one block or it may have more than one block. Now, this data that is mapped to a unique set, once it comes to the set, it can be kept in any of the blocks in the set. Okay, that's not mapped to a unique block as such. The mapping is to exactly one set. But inside a set, if there is more than one block, the data can be kept in any of the blocks. So based on the number of blocks in the set, okay, caches are organized into three kinds. So what is the basis for the organization? The number of sets in a block. Okay, the three kinds are direct map, n-way set associative, or fully associative. These are the three different cache organizations. Now, what is direct map? In direct map, we said that the organization is based on the number of blocks in the set. So we are actually going to see how many blocks are there in a set. So if you see, each set contains exactly one block in direct map. What is the number of blocks in a set? The number of blocks in a set is called n. So n is equal to 1. Each set in a block, each set contains exactly one block. So n is equal to 1. All right. Now, what does this imply? This means the number of sets is equal to the number of blocks because each set contains only one block. Okay. So we know that the number of blocks is equal to C by B. That number of blocks and the number of sets will be the same. Okay. So we said in the previous slide that each main memory data word maps to a unique set. I told you must remember that each main memory word data word maps to a unique set, and exactly one set. So if when you say the number of sets is the same as the number of blocks, now it means that each main memory address maps to a unique set and hence to a unique block, because each set contains only one block, it maps to a unique block. Okay. Now coming to the next one, n-way set associative, also called set associated. Here each set contains n blocks where n is not equal to 1. Okay. Each set contains n blocks, n is greater than 1. Now the number of sets is equal to b. B is what? The total number of blocks in the cache divided by n, because there are n blocks in each set and b is the total number of blocks in the cache. So total number of blocks in the cache divided by the number of blocks in each set will give me the number of sets. So now what happens? Coming back, each data word can map to a unique set. Okay, so it is mapping to a unique set, but inside that set there are n blocks. No, inside the set there are n blocks. Now once it comes to the set, we know which set it is in, but inside the set it can go to any one of the n blocks. So it's not a unique block anymore. It is to a unique set, but inside the set there are n blocks. So a particular main memory address can go to any one of those n blocks. Okay. Now coming to the third kind, fully associative or associated. There is only one set. Okay. There is only one set. So here now S is equal to B. Sorry, S is equal to 1. So only one set. So S is equal to 1. So what does this mean? It means that since there is only one set, any main memory address can map to the single set. Inside that single set, how many blocks are there? There are B blocks. Okay, because the entire cache is organized as one set, and we know that there are B blocks in the cache. So the entire B blocks are there inside that single set. So the particular main memory address can map to any one of those B blocks. Okay. If you see here, what did we say? We said that there are S is equal to B by n sets, and since inside a particular set there are n blocks, the main memory address, the data maps into, the data goes into one unique set. But inside that set, since there are n blocks, it can go to any one of the n blocks. This is a bigger version of that. What is that? There is only one set. So all the B blocks are inside that one set. So the particular main memory address can map to any one of those main blocks. So this is from this particular book, and thank you. We will continue this lecture in part 2.